Hello, good morning, good evening, good afternoon. This is Mr. Hill. This is going to be a little bit of a short one simply because uh, the practice in itself is actually going to help you further understand what's going on. We're dealing with solubility curves, applications, if you will. And this is Mr. Hill again with eighth grade science. All right, we look at this situation here, and we're going to take potassium chloride, for example. All of these are solubility levels for each compound. So each compound has a certain level of solubility to it that it dissolves in water. And this graph has it where we're looking at 100 grams of water, where each gram of each compound is dissolved in. We're going to start with KCl just because it's the one I picked. All right. And the way things work is that if you hit any of these temperatures, for example, any of these temperatures hit that line, that the compound you want for the solubility, that will be considered saturated. That is like the middle area, saturated, because there's unsaturated, saturated, and supersaturated. With that being said, let's say I have 40 degrees, and I want to know at 40 degrees what potassium chloride, how much would dissolve at 40 degrees. That would be 40 grams. But if I want to know if 40 grams of KCl dissolve in 100 grams of water, at 40 degrees, would it be saturated, unsaturated, supersaturated? We could rule that it'll be saturated because I hit right at the line. So we look at it, anything that's saturated right there, anything above that line, if it was 41, 42, for example, it would be super saturated. And the same goes with any of those lines. But since we're looking at potassium chloride, we're going to stick with potassium chloride. And the same is true for anything beneath the line, or like the area under the curve, if you will. It'll be unsaturated. So the area above the curve or the line is supersaturated. Anything beneath it is unsaturated. All right, let's move on. So here's some examples of some other situations here classifying. So we have for the first one 80 grams of NaNO3 at 30 degrees, which is sodium nitrate. So let's look at where it intersects 30 degrees at 80 grams. And if we look at where the line is, which is where it's at, we can already tell that because it's below the curve on the line, it's going to be unsaturated. So for the second one, which is 45 grams of KCl, which is potassium chloride, at 60 degrees, let's go ahead and look at where that's lining up at. All right, it's right here, and that is 60 degrees, lining up at what looks like 45 grams. And let's see where KCl is. It's right there. So it's right at the line, so it's saturated. And be advised, this is not an exact science per se reading graphs. The numbers may vary a little bit, plus or minus a number, because you're reading it best on how well you can interpret it. The more definitive the graph is, the more you can pinpoint where it's at. All right, so we got the next one, 30 degrees of KClO, which is basically potassium chlorate. And we can see right there, we intersect 30 30 degrees Celsius at 30 grams. And we see where we see where potassium chlorate line is. It's above the curve, so it's super saturated. Let's see for the last one with the lead nitrate. And we have, I'm not sure if that's lead nitrate, lead nitrous oxide, but PbNO3, 2. All right, so 70 degrees, so 70 grams at 60 degrees. Look at where it lines up. Where is the graph for this compound? Oh, it's right there. Let's take a look. Oh, it's beneath the curve, so it's unsaturated. And that is how you're looking at it. You want to use the X and Y grid setup. So you start at the origin 0. When you read the graph, that is, look at the temperature, go up. So you're running up to where the grams are. And look at where they intersect. And then you determine where the line is, which is right here. In this situation, for number 4, for example. And if it's beneath it, it's unsaturated. It's above it, it's supersaturated. If it hits the line of that compound, it's saturated. All right, let's describe what's going on here. It's a little bit tricky. 100 grams of NaNO3 at 50 degrees in water. This line right here is still on the graph, and so is this line here. This point is technically beneath the line. It's not above it. We don't know it's above it because it's off the grid. This, in this situation here, this point is considered beneath it. So it's unsaturated. It all dissolves, clear solution. Now let's look at this situation here. A cool solution, a very slow to cool, which it is, sodium nitrate is. If it cools down to 10 degrees, let's look at what's going on here. That's 10 degrees, super saturated. And then a quench solution, an ice bath, 10 degrees, will make it saturated. I'm just giving an example of a compound here that under certain conditions, if it cools down slowly, it will behave this way. Some solutions do behave differently, and when they cool, they will actually begin to um, move differently because heat does affect how well something actually dissolves. So if you slow down something dissolving, it may become supersaturated, and then as it cools down at a higher rate, like 20 grams, 10 degrees, it'll be saturated. So how to use solubility graph? You identify the substance with a given solubility, which is in volume itself. Sometimes you may have as grams per 100 centimeters or grams per milliliter. And both of those units are volume in itself, three-dimensional. You look for an intersection of the solubility level and the temperature as all times. These questions right here, let's look at these real quick and you'll see the same thing. How many grams of NaNO3 would have been needed to saturate 200 grams of H2O at 40 degrees? Well, if we take a look at this and let's look at what's going on. Well, I'll just make a long story short for you. It'll be like this. It would be 210 grams. It's because you're using cross multiplication. If you go back and you look at where NaNO3 is, and you look at saturation of 200 grams of H2O. So let's find it. It's kind of small. Sorry about this. Here we go. And let's look at how far it only goes up to 140 because we can't find that. So let's go ahead and let's look at where it's at the temperature. So let's start at 0. Let's go to 40 degrees and let's go up. All right. Let's not try to look for it with grams. Always start at 0, 40 degrees, the temperature, go up, temperature. And when you hit it, it's about 105. Well, what's 105 over 100 equal to X over 200 uh, grams of H2O? Because it's going to be the grams of the solute over the grams of the solvent. So that being said, you get this right here. And that's how you solve 210 grams. The next one, because it's 105 over 100 equal to X over 200, and get you 210 grams. That's your X would be. The second one is 55 grams of potassium chlorate are mixed with 100 grams of water at 55 degrees. How much will not dissolve? Well, how much would it not dissolve? Well, let's see, first of all, where does 55 degrees get you at with potassium chlorate? So that is going to be the KClO3 right here. That is at, look like 25 degrees, right? 25 grams of KClO3 or potassium chlorate. 25 grams of potassium chlorate is at 55 degrees Celsius. So if we got a question with that, we take 55 minus 25, they give us 30. So the answer is 30 grams. 30 grams that would not dissolve. The next one at 10 degrees is telling us about 125 grams of potassium iodide are mixed together with 100 grams of water. How much more must be added to saturate it? Well, let's start at 10 degrees and let's go up till we hit our potassium iodide, which is which is Ki. So that's way up there, right? That's at 100 and that's like 135 grams at 10 degrees. They want and we I at it, we're hitting it right there. We want to saturate it. We have to go over it. Well, not saturated. We want not saturated, excuse me. That'd be super saturated. Going a little too fast. So if I go here and I'm at 125 grams, I'm actually unsaturated. But 135 will be saturating it, right? If I'm at 125, I'm unsaturated. That'd be a difference of 10, which is how I got it. 135 minus 125. Now the fourth one is a little tricky because asking us about potassium chlorate, and they want to know how many grams are needed to make a saturated solution in 50 grams of water at 35 degrees. All of these here, these saturation rates and everything else, is at 100 grams of water. So let's go at 35 degrees. Let's start here. And let's go to our K. Let's see. Let's go to our potassium chlorate again to get an understanding. So I'm hitting potassium chlorate right here. And at that level of potassium chlorate, 35, it is hitting, let's say, around 14. That's where it appears to be. Because potassium chlorate needed to make, that's at 100, right? So half of that will put us at, well, hold on a minute. Let's not skip ahead. I have 35 degrees here. I need, let me find out how much it's going to be over to make it super saturated. Let's look at my work real quick. All right. So 50 grams of that minus 36 grams is 14 grams in 100 grams of water. Half of that will be 50 grams, which means it'd be 7. So we can see from the graph that's 100 grams of water at 35 degrees Celsius to make a saturated solution, while 14 grams. Half of that only be 7. All right, with that being said, let's go ahead and do the assignments, solubility practice 1 and 2. Send me questions. Also, I did uh, give an extension on the assignment that gave people a hard time with the Google Drive document that we do today. Thank you for watching and have a great day.